Hi guys, welcome back to my channel. Today we're going to be looking at some vector basics, starting off with a unit vector. So let's say that we've got this vector here, A, and it's acting in this direction. So a unit vector is acting in the exact same direction, but it only has a magnitude of length 1. So we're going to write this using a little hat to represent the fact that it's the unit vector. Now we also have unit vectors that can be operating in the x and the y direction. So when we have a unit vector operating in the x direction, we call that the unit vector I. Similarly, when we have the unit vector acting in this direction here, in the vertical direction, we call that the unit vector j. So say for example that we had a vector where a is equal to 2, 1.3, then we can also represent that using 2i plus 1.3j, and it means the same thing. So here I have a unit vector, and we can write this unit vector using 6i plus 3j, which remember is just going to be the same as saying 6, 3, or if we were to write that as a coordinate as 6, 3. So same information here. So now what we want to do is we want to go ahead and calculate the length of this line here from those points. So we can do that using Pythagoras' theorem. Here we have our bottom side, which is equal to A, and this length here, which is equal to B. And so our magnitude of U, which can be represented using these straight brackets, is going to be equal to the square root of x squared plus y squared, according to Pythagoras' theorem. So that's going to be equal to the square root of 6 squared plus 3 squared. 6 squared is 36, 3 squared is 9, 36 plus 9 is going to be equal to 45, so that's going to be equal to the square root of 45, and that's equal to 3 root 5. So that's how we can find the magnitude. How then do we go about finding the direction that this angle is, that this arrow is acting in? Well, we can use our angle from the x-axis here to represent that direction. When we choose to represent a vector using its magnitude and its direction rather than its x and y components, this is called polar form. So usually we are used to using straight brackets around these vectors, but we can also use the letter r to represent the length of this line here, or the magnitude of the vector u. So we can find this really easily because we've just used Pythagoras' theorem to do it. So this is going to be one of our special equations where r is equal to the square root of x squared plus y squared. So now what we need to do is we need to go ahead and we need to work out this angle here coming up from the x-axis. So to do that, I have my adjacent side length here and my opposite side length here. So tan of my angle is going to be equal to the opposite over the adjacent. And let's write this in using our x and y's now. So my opposite side is going to be equal to this vertical component, the y component. So we can write tan of our angle is going to be equal to y over our adjacent side, and that's going to be equivalent to our horizontal component x. So if we wanted to find the angle is going to be equal to the inverse of tan of y over x. So let's go ahead now. We already know that our magnitude is going to be equal to 3 root 5. So let's go ahead and let's determine this angle. Substituting into my formula, I get a value of 26.57 degrees. So what we can do, rather than representing x and y components, we can do this now using our polar form. So we're going to use brackets, r, comma, theta to do that. So for ours, we have a value or a magnitude of 3 root 5, and our angle is 26.57 degrees. Let's go ahead now and let's use another example. A bushwalker walks 16 kilometers in a direction of 50 degrees. So here you can already tell that they've given us the magnitude and the direction. So that means that we're going to be operating in polar form. The bushwalker then walks 12 kilometers in a direction of 210 degrees from the x-axis. So let's go ahead and draw this scenario. So now we need to determine the resulting position of the hiker, giving magnitude and direction from the starting point. So with Cartesian form, or when we have it in our horizontal and vertical components, all we need to do is we need to add the two vectors to find this resulting force here. So I'm going to draw in this line here. So this is the length now that we're trying to find. However, you can probably already tell that if we were just going to add our two magnitudes together, 16 and 12 are going to make 28. So that would be if we were to add this in a linear way, this would be adding up to 28, which I'm sure you can appreciate that's not exactly going to be the same thing here. So unfortunately for us, we need to convert back into Cartesian form, back into its component form, before we can actually add the two vectors. So there's two formulas that we can use to do that. So the first formula that I'm going to use is x is equal to r cos theta. So r is going to be my magnitude here, and theta is going to be my angle. So this has come from SOHCAHTOA. So just as an aside, drawing this triangle here, if I was to draw this is an angle of 50 degrees, magnitude of 16, and I want to find this x component here, that's equivalent to my adjacent side. And so I can write that cos of the angle is going to be equal to the adjacent side over the hypotenuse, or that cos of the angle is equal to x over r. So since we have theta and since we have r, rearranging for x, we get x is equal to r cos theta. So we can do something similar and we can determine that y is going to be equal to r sine theta. And this is because we'd be looking then at the opposite side, so this length here, as opposed to the adjacent side. So let's substitute those values into our formulas and find the horizontal and vertical components for both of our vectors. Now that each vector is back in its component form, we can go ahead and add each of the x components and then add each of the y components to get the final position of this vector here. So if we were to try to find the point here, this is going to be at negative 0.11, positive 6.26. So we can go ahead now and convert this back into polar form by using our Pythagoras' theorem and using our tan function to find each of these values for the magnitude and direction. So finally we have our angle here. So to represent this using polar form, we're going to use 6.26 at an angle of negative 89.01 degrees. Right, so that's how we use polar form to convert to Cartesian form, and how we can use Cartesian form to convert back to polar form. Also in this video, we had a look at the unit vectors for the horizontal component, which is I, and we had a look at the unit vector for the vertical component, which is J. All right, guys, I'll see you in the next video.